modular toric law.
Thank you. Thank you very much for the invitation to this conference or workshop, and also, I'd like to thank the organizer for inviting me. And so, my topic is about quantum cohomology of toric. And because I have given many similar talks in many occasions, so I apologize if you already have heard my talk. But
would you mind speaking a bit louder?
Louder, okay. I have given a talk many times of this thing. So perhaps you have seen similar talks. But recently I finished my paper, and it's not on the archive, but you can see my homepage. So I think this is some hidden link. .pdf. So maybe probably will appear soon in the archive. But you can, if you have any comments, please give me. And so this talk will be somehow closely related to yesterday's talk by Kontsevich, and kind of example of his semi-orthogonal decomposition. So first, in the first part, I'd like to talk about some motivation or reason for the toric mirror symmetry, and so let's consider Cm mod C star Cr. So this is some toric variety, orbifold in general. And in this talk, I just consider all toric orbifold of this form. So it is a GIT quotient of some vector space by some torus. And I just write this torus C to the R by K. And there is natural torus action on this toric orbifold by construction. I have an action of this torus, C star to M over C star to the R, and this is T. So so I want to consider somehow T-equivariant Gromytin theory of toric orbifold, and of course somehow. So this is a quotient of C star to M by K is equal to T. So there is an exact sequence. K, C to the M and T. One. The exact sequence. This is some basic exact sequence. And if I take a Lie algebra, Lie of K, and then maybe Cm and Lie of T. This is an exact sequence. And so in this exact sequence, this Lie of Tk, this corresponds to sort of Kähler parameter. So more precisely, maybe the dual of the Lie algebra of K is related to this stability condition you used to define this GIT quotient. And this omega is, so dk, maybe real part. And the dual of this. And this will be isomorphic to, in a simplest example like toric manifold, this will be just H2 of X. Maybe in the orbifold case, maybe H2 orb of X, or maybe other things. And then this part will be related to the equivariant parameter. And yeah, so equivariant parameter is an element of dt star, which I denote by a notation lambda, and this will be equivariant cohomology of a point. Okay. So this is just some explanation for geometry of toric variety. And somehow I want to consider some combination of Kara parameters and equivariant parameters. And then I get the following. So I want to have I have some equivariant quantum d modules. So this is something. This is the following. So I want to consider trivial equivariant cohomology bundle over K check, some dual torus of K. K was a torus defining, so maybe I just call that Cm mod mod K. This is a torus defining toric variety over K. K check, this is a H2 of X with coefficients in C star. And I consider this just a trivial HT star X bundle over K check, and with some flat connection, so-called Dabrovin connection. So this is given by yeah. So I introduced some notation. So this K checks. This is a torus where equivariant Novikov parameter lives. So I have some parameter Q1 to QR. So where R is a rank of H2, and also use. So this is some coordinates, C star coordinates, and this is dual to basis of H2 of X. This is basis of H2 of X, and I also need to choose some equivariant lift. Maybe there is some ambiguity of choosing equivariant lift, but that's not really essential. So I have the following Dabrovin connection, which I write in this way: QA dd QA plus PA star. So there is some additional parameter Z, which was maybe denoted by U in Kontsevich's talk, and also maybe H bar in Seidel's talk. And so there is some additional parameter Z, and this is some flat connection depending on Z, and flat connection on this trivial vector bundle with fiber equivariant cohomology over this base torus. And this one is just a small quantum product. And this, yes, I forgot. Or H. This is some parameter. Some parameter. And obviously, I have the following commutation relation. So this flat connection and QB will satisfy this QA. So will this have this relation? And So this is just a property of connection. And so they form some Heisenberg algebra. And there's somehow a similar story for equivariant parameter and Seidel representation. So, what I'm going to talk. So, so there is another parameter, so the equivariant parameter. Equivariant parameter. Lambda I. So maybe I write down lambda 1 to lambda n, which is the basis of lead T star. This is equivariant parameter. And there is also some something called the Seidel elements or Seidel operators, or maybe shift operator. So x1 to xn, which is an element of Hom from C star to T. This is the basis of this co-character lattice of T, that somehow if I have a co-character of T, then that induces a C star action on the toric variety. And so each xi will be a C star action on the toric variety, and that gives you some invertible element in quantum cohomology. So I have this pair. Yeah, so originally Seidel's definition gives you invertible element of quantum cohomology. But there is some later work by Okonkov and Panharipande and Braverman and Molik and others lifting this to an equivariant setting. So this will act on the quantum D module, equivariant quantum D module. So by this notation, I mean just as a module, this is just equivariant cohomology of X. Maybe I join Z and variable, Q variable, Novikov variable. So there is some operator. So the definition is just almost the same as Seidel's element. So Seidel's operator. So, but just with respect to some action, torus action, you consider torus action on X. And you also consider additional torus action. This Z is another additional torus. C star action acting on the base of the curve. So quantum cohomology or Seidel elements somehow counts sections of some space, and you consider C star action on the base. So this is this Z.
Is it possible to give formula for xi?
Yeah. So you consider somehow for each xi, C star to the P. For each xi, I consider some bundle over P1 by somehow twisting. This will be a disk cross X and the union of this cross X. And the gluing map is given by somehow by this function. So by twist, the boundary of D2 is circle, and you can just twist it. And then you count somehow. You consider the moduli space of sections, and then you have so you have some moduli space, and then somehow you have evaluation map at 0 and infinity. And then you use this somehow correspondence to define this operator. This was the same as the original definition, but you just consider with respect to torus actions. So then what one finds is that these operators satisfy the following commutation relation. Xj. So this is something similar to, this is something similar to this one. So this is similar to this. So xj, actually, this is not linear over base ring. So the equivariant cohomology of a point, this is not linear. And you can, there is some non-commutativity between lambda and x. And this means that xj somehow shifts lambda j, by minus z. Or another way to think about is lambda j differentiates xj. So by something like zxj ddxj. So there are two ways to look at this because of this differential this commutation relation. And so maybe it is natural now to think of these things in terms of as a D module. So here it is obviously D module, but you can also think of this as a D module over X space. So where lambda is considered as connection. So I have in total I have so on this equivariant quantum cohomology I have 4 operators. So the 4 operators. So 4 operators, just a multiplication by Novikov parameter QA and this Seidel operator, and also this connection, this Z connection, and this lambda j. And they are somehow canonical conjugates. Conjugate to each other, and yes, and somehow so we want to think of quantum D module actually as a D module over the space with Q parameter and X parameters. The usual view for quantum D module is somehow this. So you consider Q and lambda as basic variables, and xj and this one as additional operators. But now if I look at somehow these 2 pairs as fundamental, or somehow, I don't know how to say, but some basic variables, then there's some different way to look at the quantum D module. So this is somehow viewpoint of Tellman, and he said that the equivariant quantum cohomology should be, or quantum D module, equivariant quantum D module is a sheaf over XQ space. Or more precisely, we can think of quantum cohomology as a characteristic variety in the cotangent space of this XQ space. Then this is somehow the space of full variable space. So then kind of quantum D module as a sheaf of XQ space will become kind of very trivial, and because maybe I.
Is it something that's easy to write down for E2?
Yes, very easy to write down. Yeah, I write some general formula and then some specialization of that case. So I have exact sequence. Recall that I have exact sequence of tori, and then I take a dual, so dual tori. So this was just a dual exact sequence. And then this K check, this was a Keller moduli. where Q variable lives. And this T check, so this is Q variable space. And this is something like an equivariant moduli. I don't know how to say, but some X variable lives. And then what I mean by this, so as a sheaf over XQ space, that means that I want to construct something over here. So the quantum D module, equivariant quantum D module is a sheaf here. Sheaf here. So in the middle. So then this is something quite easy to understand than the original one. So the original one may have bigger rank, but the point is that so maybe I write coordinates here, u1 to un. There's coordinates on the middle torus. Then the variable uj, this will be some mixture of q variables and x variables. So this might be some combination of two things. But this is basically some Seidel operators. So so uj restricted to, so if I let it act on equivariant quantum cohomology, then this will be multiplication by toric divisor plus some quantum corrections. So this is just a well-known fact, maybe I think originally due to Macduff and Tolman, and which can be easily proved. And yeah, of course, some of Macduff, Tolman show more general stuff. But in toric case, I think it's not so difficult. And this fact shows that quantum D module, equivariant quantum D module, is generated. Sorry, sorry, I forgot to say, this is a toric divisor. dj is a toric divisor. Because quantum cohomology, or just usual cohomology generated by divisors, this equivariant quantum cohomology D module is generated by 1 over this ring. Maybe you may need some localization and some completion.
Can you explain what is this? What does it mean on D module of the sheaf on this case? I don't know.
Because somehow the functions on here act on this. So this is a module over the functions on C to the M. So
as a set, which thing is one quantum D modules of C of X?
Sorry?
Just like quantum D modules of C of X as
Yes.
a set.
As I said, this was maybe, sorry, QDM. T of X was just this one. So this is.
And when you say the functions on the app, like that commutative algebra.
Yeah. Yes. So this is somehow commutative subalgebra of the yeah, and it is actually D module over this space. And somehow by this fact you can say that this quantum D module of X, equivariant quantum D module, it is just generated by just unit element, identity element over. So this is just a rank 1 local system, rank 1 local system or connection. Which is necessarily of this, given by a certain connection of this form. for some W. So for some W, which is a function on maybe some function, formal function on sister today. I'm not necessarily actual function. And this is a Lagrangian mirror. So so actually, this computation said that this W, this means that W is equal to U1 plus sum of all Ui's plus some higher ordering Q. So this is some, maybe, yes, for higher ordering Q. And moreover, somehow you can, if you consider, instead of small quantum cohomology, if you consider big quantum cohomology, then actually universal deformation space or deformation space of this W can be identified with equivariant cohomology. So, so what one can show is that some of this term can be killed by bulk deformation. So, so this can be cancelled by bulk deformation. So yeah, so somehow similar story appears also in different contexts. For example, in Fukaya Otaono's work, but somehow here I do not count holomorphic disks, but just doing some standard computing theory. And then somehow you get automatically this potential function from nothing. So this is somehow maybe I want to write this W. If I write W in terms of this splitting of coordinates, then this will be of the familiar form Q to the power L1 x to the B1 plus Q to the power L some elements EM. So so in the case of P2, you know what this is, right? So this is a usual super potential for Lagrangian mirror. So where Bi is a ray one-dimensional sort of generator of one-dimensional cones of the fan of X. So so this is how one can think, and then
So working in this equivariant setting picks out for you some one best superpotential?
Because this is generated by the identity element. So the generator gives you a choice of W. So because if you're a generator, then this is just canonical isomorphic to this, and then you just write this connection in terms of this trivialization. So this is some canonical choice. And then somehow, for example, you can go back to the usual given tau mirror symmetry by using Fourier transform. So you consider partial Fourier transform. Fourier transform. So that is, I considered lambda and x are canonical conjugate pair. So I just, so this exponential W over Z, this is a solution to this connection, ZD plus DWH. So this is a solution of rank 1 local system or rank 1 connection. And then just take a Fourier transform of this. So I consider some integral over x in t check. So maybe I choose some middle dimensional cycle, and then w on z exponential minus lambda log x dx on x. So this is Fourier transform with respect to variable x. So this has variable x and q, and I just consider partial Fourier transform. Then switch to the variable lambda. This will give you a solution of quantum D module in the usual sense, so the usual solution, given those mirror. So, so in this way, you can recover given to mirror from this consideration. And somehow, maybe not every part of this line of argument is not completely written down. For example, maybe for manifold it is, I think, no problem, but for orbifold, maybe one has to write some details, but at least this conclusion was somehow proved in a joint work with Coates and Coty and Chen. And
which statement is the conclusion?
The conclusion, this is a solution to the quantum D module. Yeah.
But not, it's not proved by this argument.
Yeah, because somehow this was something after we proved it. So in this paper, we proved mirror symmetry for toric stacks in general. And
mirror symmetry is the statement that this is the solution to the quantum module?
Yeah, this is one of the statements. And the other statement is that you have some I function, and the I function lies on the Lagrangian cone, given the Lagrangian cone. And yeah, but that is more technical statement. So, but that is essentially equivalent to this. So, so maybe this is somehow the introduction to toric mirror symmetry. And then I want to consider toric blowup or toric wall crossing. So, so recall that toric variety was defined by this way. So I choose some stability conditions for K, for the GIT quotient. Then there is some Wollan chamber structure. So so if I consider this one, this is a spaceable stability condition. And this space has a Wollan chamber structure, like this. And then, so I want to consider some wall crossing from omega plus to omega minus. Sorry, but omega minus. Well, no, I don't know. I'm just considering I fix this GIT. Just somehow fix this presentation, GIT presentation, and then the space of GIT stability conditions. Yeah, this is not like Bridgeland stability or yeah. And then yes, and then just set x plus minus as Cm omega plus minus k.
That's always something like you say the moment Politov.
Mm-hmm.
Then the combinatorial type of moment Politov.
Yes, exactly. Yes. Yeah, so there's some momentum Politov, here, and then one of the edges collapse, for example. This kind of. And yeah, maybe right. Yeah. So and then there are two cases we can consider. So. So I have this diagram in this case. You can construct a common blow-up or common somehow something that maps birationally to x. You can construct such x hat, and there is some birational map between x plus and x minus.
Hat is not toric.
This is toric also.
This is the toric.
This is also toric. You can somehow describe some toric variety somehow.
So it's singular.
This singular one is here. There's some singular one, but you can blow up the singularity and then. So, and then one wants to consider the two cases. There are two cases where this pi plus pullback of x is equal to pi minus pullback of kx minus. This is a so-called Crepant case, Crepant birational transformation, and then there is this Crepant. In this case, there are only two cases, so I have either there are three cases. Sorry, so either equal or bigger and smaller. Yeah. But switching plus and minus, I can just somehow restrict to this case. And so this is discrepant. Sorry? Yes. That's what I mean by this. So the difference is effective divisor. So so what about somehow, if I look at the mirror, so this Landau-Ginzburg potential was defined on K somehow, was some family of potentials parameterized by K check. So I have some dual toric variety. This is 0 plus and 0 minus. So this GKZ fan, some secondary fan, defines some compactification of K check, and I have this some compactification of this base space of Landau-Ginzburg model, and maybe more precisely, I also have equivariant parameter. But the previous construction gives you a family of Landau-Ginzburg potential, so over here. So this gives you, and then this gives you some Gauss-Manning system of W. This is maybe I just erased, but this is somehow the D module whose solutions are this equivariant oscillatory integral, exponential minus log x are solutions. So some D module such that these are solutions. And then obviously somehow we already, maybe I want to state the theorem. So Kotzkolty and myself understand. This Gauss-Manning system of W completed at 0 plus minus will be the equivariant quantum D module of x plus minus, x plus minus. So this is something, of course, this would also follow from the previous argument, but the method is different. But so if I look at this Gauss-Manning system generated by these solutions, and then take a completion at these 2 points, then that is a quantum D module. And this is one statement.
In the argument you gave earlier, where does the completion appear?
The completion was actually appearing when I was saying that the equivariant quantum D module is generated by 1 over a certain completion of, yeah. So there I need completion. And so somehow it is not easy to communicate these 2 points. So because of this completion problem. So I want to compare the 2 points, but there may be 0 convergence of radius. So then you cannot compare. And yeah, but actually you can. So that's something I want to say. So so in the Crepant case, so first maybe I say Crepant case. Crepant case, this is something old work, but so quote myself and Jiang. We show that somehow these two are quantum D module of x plus are related to quantum D module of x minus. Under analytic continuation, you can analytic continue along this curve and then compare them and Crepant case. And also some gamma integral structure, the integral structure coming from K theory also match up by Fourier-Mukai transform. That was old result of Borisov and Horia. And so their result is about GKZ system, but you can translate their result in this context and see that these gamma integral structures are preserved. And today I want to concentrate on this Crepant case. And so the discrepant case, you have the following. So so discrepant case, so the problem in the discrepant case is that the rank of cohomology of x plus is bigger, strictly bigger, x minus.
You see, this Crepant case result in
Yeah.
the theorem
Yeah.
is that on this path, the structure is something constant.
No,
Path,
no.
but so the right-hand side is the isomorphic, right?
Yes, yes. Are you talking about this?
Yeah. And then the left-hand side is completely different point. I mean,
Yes.
your theorem.
Yeah. Yeah, so this is some analytification of, I don't know, analytic version, which you can analytify. So, so this is only formal version, which is originally only formal version, but you can prove some
So
convergence.
it means that you can lift this formal value to analytic value so that this has
Yes, yes, yes. Actually, yeah, maybe more precisely, when we proved this, we didn't know the convergence, but somehow we only know the convergence in a formal neighborhood of this curve. So, but now we know the convergence, so everything is convergent. So the technical key point is the convergence result. This is also joint work with called T and Zen. And this mirror isomorphism, this one, so this isomorphism Gauss-Mann W hat 0 plus minus QDM star X plus minus can be defined over the following convergent paraseries ring. So this is slightly strange ring because this is convergent in Q and lambda, the base variables, but is not necessarily convergent in Z variables. So I have some natural basis, for example, given by algebraic differential forms here, and then I have natural basis given by basis of cohomology, and then look at the transition matrix. And the entries are defined here.
So this convergence with Q and R lambda is just usual classical topology.
Yes, yes, yes.
It's not this rigid analytic function.
No, no. And somehow, I don't know, for my purpose, the convergence is kind of quite essential. So otherwise, it is somehow, I'm not sure. Maybe there may be some way to understand
this.
This
Is the homomorphism of Z is coefficient holomorphic function.
Right, exactly, exactly. So, but this somehow, it is not possible in general to improve this into convergent in Z. So this is, and also this also implies that this quantum cohomology itself is convergent, because quantum cohomology doesn't depend on Z, so you can prove the convergence of quantum cohomology. And now, now I want to say the result for discrepant case. So before I define quantum D module bar equivariant to be quantum D module. So X with formal power series in Z. So yeah, maybe I'm considering analytic version, and then analytic version is completely analytic. So it is polynomial in Z and also analytic in lambda and Q. And I just tensor with this formal power series ring in Z. And then I can compare the two. So maybe I take this picture.
The existence of this analytic version,
Yes.
Is that a non-trivial statement, or is that?
This statement, or?
The fact that there is such a thing, which is quantum D module analytic.
Mm-hmm.
Is that comes with definition? Do you have to prove something to get that?
You have to prove something because the quantum product may not be convergent. So yeah, it is generally expected to be convergent, but you have to prove.
But that's this convergent statement.
Yeah. Because somehow this also implies that quantum D module itself is defined over quantum this convergent per series ring. And then the main theorem. So this is one first result. So this quantum D module formalized will have some formal decomposition bar plus something else. And so this R, I don't know how to say. I know how to say, but somehow it's not so easy to state in a geometric language. But there is some D module with pairing. So this is some orthogonal decomposition with respect to pairing. But you have this decomposition, and somehow you can compare the two. This is analytic in the Q and lambda direction, but formal in Z direction. So, but this is just Q space, so you can compare the two. And somehow this is somehow related to maybe generalization of Gonzalez, Woodward. So they show that instead of quantum D module, they show that the quantum cohomology splits. So this is some generalization, and then there is another result of Costa and Shoemaker, and there's some announced work by Lee and Ling Wan, and they. At least it's Acosta Shoemaker, they prove some relation between I functions. And then Li Ling Wan, they claim that some similar relation between quantum D module. I guess essentially the same, presumably, but Yeah, so yeah, then finally I give you somehow the semi-orthogonal decomposition and analytic lift. So before that, I give you some example. So this very simple example of blow up. So let's consider x minus to p1, p4, and x plus is a blow up of x plus x minus along p1. Some example. Both are Fano manifolds, and you want to study the relationship between the two. And in this case, the potential function, if I write in some coordinates, this will be Q1, Q2 plus maybe the precise form is not important. X2, X3, and something. And then I have this kind of picture here. Maybe I draw it again. So here I'm using coordinate near, I think 0.
For something like P4, oh, is that W for X plus?
Both, because the W are common, right?
Yeah, but so like, how for something, I mean, before you began with something like P4, and then you had some procedure for producing a W.
Mm-hmm.
And why did you end up with such a weird W for P4?
Yeah, because this is because I'm considering bulk deformation. Yeah, so to kill the somehow if you just construct in the usual way, then there will be many terms. But there's 0 minus. Oh, sorry, I'm writing wrong. So this is Q1. This is Q2. There's another set of coordinates. Maybe I change coordinates. T is Q1 inverse, and Q is Q1, Q2. Then there's this coordinate center that's 0 minus center and 0 plus. And so actually there is some, as Alessio said, there is big quantum cohomology business. So Q1, Q2 corresponds to the small quantum cohomology of X plus. So this has Picard rank 2, and Q1, Q2 are curve classes. Curve classes on X plus. And Q1 is somehow the curve which is contained in the exceptional divisor and which collapse under this blow-up. And this T, and this T, Q is some curve class on X minus, and then this T is H class of H6 on X minus, which corresponds to the Poincare dual of this blow-up center P1. Then, maybe I have only 5 minutes. And then in this setting, somehow, if you look at the critical values of W, and then somehow you know how to, if you think about the Fukaya-Saito category of the mirror, you know how to decompose this somehow, how you get some semi-orthogonal decomposition from this. So in this case, critical values, configuration of critical values. This is some similar picture appeared yesterday. So I have something here near t equals 0. near 0 minus. Near 0 minus. And I have critical points like this. And yeah, in this case, somehow the this is codimension 2 blow up. So I have codimension 3 blow up. So I have two blocks, but in general, somehow you have n blocks, as we see yesterday. And this is something like 2i e to the minus 1/2. And this is something like 5q to q1 to the q to the 1/5. And then somehow you see that maybe if I take some kind of semi-orthogonal decomposition, then they will correspond to exactly to some Orloff decomposition. So this corresponds to k of x minus, and this corresponds to k theory of blow-up center P1. And this is k of P1 twisted by -1. So twisted by some O minus 1 of the relative O1, relative O minus 1. So finally I can say the so there is some analytic lift. So if you, maybe you can also consider in terms of Fourier transform. But if I'm just working on the regular side, then there is some notion of analytic lift. So if you have this, the previous theorem, some formal decomposition, then that can be lifted to some isomorphism like this. D modulo x minus plus some analytic. So this is 2 times some sector. So I is an angular sector in the z-plane of angle bigger than pi. So this is some sector. Yeah, I'm sorry, I didn't talk about differential equation in the z direction. I'm sorry. So also consider non-equivariant quantum D module instead of equivariant one. And maybe there will be some interesting structure in the equivariant Stokes structure, but I don't know much about this. And so if you fix some angular sector on the z-plane, there's some differential equation also on the z-plane, and this preserves the differential equation in the z direction. And you have some unique analytic lift over some angular sector. And the result is the following. So the theorem. So a weighted blow-up along torics substack, and also assume some technical condition that x plus minus is compact and weak funnel. So previously there was no assumption, but now assume that compact and weak funnel. maybe this condition would be unnecessary, but I don't, there is some technical issue. So then there is an analytic lift. So this analytic lift depends on the point Q and also this sector I, corresponding to Orov. So to the Orov SOD. So K group of X plus will have some decomposition into K cross Z. I'm just following the notation of Orov. So there's some, this is actually originally a decomposition of derived category, but you can go to the K theory. And then this is a, and this KZ sub something is some twisted by relative of 1. And then you get, so this decomposition will induce at some point and this analytic lift. So I stop here. Thank you.
Questions?
So I'm very confused about what happened in this last board.
Mm-hmm.
Because up until this board, you were always discussing a model on the toric variety.
Mm-hmm.
And now you start discussing a model on the.
Yeah. A model on that. Yeah, yes.
So why is that?
Because so the A model is given by, of the toric variety is given by this exponential integral. And if you think about what is the integration cycle, the natural candidate is of Fukayasaito category. So, so at least on the homological level, the space of solutions to this quantum D module is somehow comes from the Fukayasaito category of the mirror.
So you never actually use the categorical aspects.
No.
But just the
Yeah.
categorical.
Yeah. I think some of the categorical aspects are, for example, studied by Kazarkov and his collaborator. So
it's comment. I think this Duke paper, we calculated grow up this project space and some sub-project space, something similar to your calculations. And if my memory is correct, we have some new critical points whose variation is closer to this original basis. So it's somehow probably related to this definition.
Yes, exactly, yeah.
Other questions or comments? If not, let's go to Hiroshi again. And there are some professionals in the canteen, so we'll resume it again.